Alright guys, in this video I'm going to go over the graph of tangent and cotangent and their transformations. So if we were to fill out these table of values for tangent, you can start with 0. What's the tangent of 0? That's 0. Pi over 4 is 1. Pi over 2 is undefined. And you could just keep filling these values out, and then you could try and graph it. It's going to be a little hard to graph just using these kinds of values. So I want to show you what it looks like off the bat. It looks something like this. And if you don't know how to graph undefined, that's rather normal. So we'll skip that. It'll look something like this. So negative 3 pi over 4 is 1, and negative pi is 0. So we kind of have this we don't know where to connect the dots, and we don't really know so far how to deal with. So let's go to Desmos and see what it tells us about undefined values and what it looks like. So if we go to Desmos and we graph tangent, you'll actually know that at where it's undefined, at tangent of pi over 2, it's undefined, there is a vertical asymptote. So we see those values of negative 1, 0, 1. That's kind of our low, middle, high. And then at pi over 2, we have our vertical asymptote. And at negative pi over 2, we have our vertical asymptote. And if you notice, it repeats again. We have negative 1, 0, 1 asymptote. You go backwards, 1, 0, negative 1, and there's probably going to be an asymptote back there. So the period, how often does this repeat? It's a repeating thing. So if we were to scrunch in, you notice that it repeats over and over. It's the same thing. Just like sine and cosine. So what's the period of this? Well, if you go from negative pi over 2 to pi over 2, that's 2 pi over 2s, or that's just a length of pi. Okay, so that's the period of this tangent function. So if we were to finish graphing this off, again, at negative pi over 2, or basically where it's undefined, we have asymptotes here and here. And every pi, so if you hop a period of pi, you can get another asymptote. Okay, and in between, you're going to get a 0. So it looks something like this. And then you could finish. Remember, the graph kind of tends towards the asymptote, like so. So that's it. That's the graph of tangent. Pretty simple. Let's talk about some of the properties. We can do vertical stretches on tangent, but there is no such thing as an amplitude. Okay, so the word amplitude is not appropriate here, but we do have something called vertical stretches as usual, and we will deal with those. So vertical stretches only. What's the period? The period is now pi. So sine and cosine was 2 pi. The period for this is pi. And if you were to do some kind of a horizontal compression, we could say it's going to be pi over b, because there would be a compression of b. Compression, a horizontal compress of b. Okay. One of the most important things I want to tell you guys, where you start. So this 0, 0, it starts on a 0. Pi units later, it ends on a 0. So that's going to be one of the most important things that you want to remember for graphing. So starts at 0, 0 and ends at 1 period, comma 0. Okay. One more thing, it's always increasing except at the asymptote. So what do I mean by it's increasing? It's going up from left to right. It's climbing up. So this is a increasing function. All right, so that's the graph of tangent. If you want to kind of remember a little trick, most people tend to define tangent from negative pi over 2 to pi over 2, and that actually makes the most sense. So if you want to use something like that, you could say asymptote low, 0, high, asymptote from negative pi over 2 to pi over 2. And that would be kind of like asymptote low, 0, high, asymptotes. It kind of spells out the word aloha. So that's kind of a interesting way of remembering it. And then if you were to record a table of values, you would say xy. You would put 0, 0 at the center, negative pi over 4, negative pi over 2, pi over 2, pi over 4, and it would go asymptote, low, 0, high, asymptote, or undefined. Okay, so we're going to use that if you decide to go the tabular method for transformations. Now let's take a look at the function of cotangent. Well, if you kind of use the same idea as the previous reciprocal functions, notice here at 0, 0, if you flip a 0, that becomes an asymptote. So here, there should be an asymptote. Where there was a undefined value for tangent, that was actually where it was 0. So that's where cotangent was 0. Okay, so if tangent's undefined, then cotangent 0. And again, back to here, where tangent is 0, then cotangent should be undefined. So this is how you would graph I mean, like, this is just one way of thinking about it. And then notice that it also has a period of pi. It goes from 0 to pi right here. So every pi, we should expect an asymptote. So we might expect another asymptote here at 2 pi, another asymptote here at negative pi, another asymptote here at negative 2 pi. And in between, here, here, and here, there should be zeros, because that's all the places where tangent is undefined. So where tangent is undefined, cotangent is 0. Where tangent is 0, cotangent is undefined. What about the values in between? If you look at pi over 4, that's 1. Well, what happens when you flip a 1? Well, you get a 1. What happens when you flip a negative 1? Well, you get a negative 1. And it's funny because the ones look like they just produce the same value, but when you look at the graph, it actually looks like it's decreasing now. It's not looks like it's decreasing, it is decreasing. Again, I'm going to graph cotangent. It has asymptote, pi, a period of pi later has another asymptote, a period of pi later has another asymptote, and in between those asymptotes, there are zeros. Just like sine cosine, it's got a high of 1 and a low of negative 1. And when I say high, it's not really the amplitude, it's not the amplitude, it's just like a point now. It's just a regular old point. Properties of cotangent. It also has no amplitude, so I don't need to write that, but just remember it also has a period of pi, and it can also be stretched horizontally by pi over b. So this is a b horizontal compress. And one of the more important things, tangent started at 0, 0. It starts on a 0, okay? Whereas a cotangent, it starts at 0, comma, and I'm going to write this down. This is not a point, but I'm going to put asymptote. And then it ends at 1 period later, comma, asymptote, because that's going to help you remember how to graph it. Now, if you want to produce a table of values, you kind of like tangent, you could choose to start at negative pi over 2. This one, I think people prefer to start this one at 0. So you go from 0 all the way to pi over 2 here, pi over 4 here, 3 pi over 4 here, and then we get asymptote, high, 0, low, asymptote. So that's going to be something you want to remember. All right, so let's take a look at example. This example number 1, y is equal to 3 tangent 2x minus pi. Remember, whenever you have a horizontal stretch right there, you always need to factor it out from the terms inside. So we need to factor out a 2 from the 2x and from the pi, so we could observe the horizontal shift. So that's going to be 3 tangent parentheses 2 parentheses x minus, and then when you factor, that's going to actually be minus pi over 2. Remember, factoring is division. So when you factor pi from 2 from pi, you're doing pi over 2. So first of all, let's start off with the table of values that define tangent. For a regular tangent function, y is equal to tangent of x. Remember, from negative pi over 2 to pi over 2, it was asymptote, low, 0, high, asymptote, and I think these were every units of pi over 4. So negative pi over 4, 0, and then pi over 4. Okay. So this is the tabular method where you just do the transformations one by one. We have a vertical stretch of 3, we have a horizontal compress of 2, and we have a horizontal shift to the right of pi over 2. So let's start with vertical stretch of 3. That's multiplying all the y's by 3. And then let's do a horizontal compress of 2. That means we're going to divide all of these values by 2. And then the last one, we're going to shift to the right by pi over 2. That would take all the x values by right pi over 2. And you guys are pros at this. It's just the heavy lifting that is just a lot of busy work. So I'll fill in these values for you. All right, guys. So now we're done with that. You could check these values. At pi over 4, we're going to have an asymptote, and 3 pi over 4, we're going to have an asymptote. So you want to check that. I probably shouldn't have highlighted that entire thing. Pi over 4, we're going to have an asymptote, and 3 pi over 4, we're going to have an asymptote. And then we're going to have these values correspond to my tangent function. I want to show you guys a different way that I personally like to do it. You do have to remember how tangent starts and ends. So let's first talk about the transformations, and let's talk about the period. The period for a tangent function is normally pi. So the period is normally pi, but we compressed it by 2. So it's now pi divided by 2. That's my period. There is a horizontal shift of pi over 2, so it's going to start at x equals pi over 2. One period later, it's going to end at pi over 2 plus pi over 2. That's going to be x equals pi. So let's mark that out. And again, just like with sine and cosine, you want to mark it out in intervals of 4. So we're going to start at pi over 2. And again, I'm going to use intervals of 4. 1, 2, 3, 4. That's going to be my pi over 2. 1, 2, 3, 4. That's going to be my interval for pi. This is where we start. This is where we end. Now, before I start graphing points, I want to also take into account that we have a vertical stretch of 3. So instead of marking out 1 and -1, we're going to look at 3 and -3. That's going to be how high and low the points are in between, instead of 1 and -1. So start and end. Tangent starts on a 0. You want to remember that. Tangent starts on a 0. So we have 0, 0. Every pi unit, we're going to have a 0. So if we go every pi over 2 units, we have a 0. So every pi over 2, we have a 0. So we're going to have another 0 right here. If we go back 1, 2, 3, 4, at negative pi over 2, we're going to have another 0 right here. And in between all of those zeros, guess what we have? We have an asymptote. Another asymptote here. We have another asymptote here. And remember, aloha, asymptote, low, 0, high. So we're going to low, but the low is no longer at -1. Now it's at -3 and 3. And then when we graph it, it's going to look something like this. -3 and 3. Graph it. So there we go. We got 2 full periods. Where are my asymptotes? Let's mark those out. This is going to be at x equals -pi over 4. This one's going to be at x equals pi over 4, because that's half of pi over 2. That's going to be at 3 pi over 4. And that's important because I might ask for something like domain, or I might just straight up ask for where the vertical asymptotes are. So the domain of this function, we say x cannot be defined where the asymptotes are. That would be at x cannot equal pi over 4. The next one was 3 pi over 4. You can even talk about the one before it. That was negative pi over 4. And if you notice, every time it's going up by pi over 2 units. So we could just come up with some kind of a general formula like pi over 4 plus n times pi over 2, because it's increasing by every pi over 2 units. And then you could add something like where n is an integer. Okay, so that's basically telling us where the function is not defined. If you look at this function, the range, it goes all the way down to -3. So this function goes all the way down, and it goes all the way up. So it's defined for all values. So we could say the range is all real numbers, or in interval notation, -infinity to +infinity. All right, so we're going to look at another example. This time it's going to be a cotangent function, and this time that's loaded with all kinds of transformations, so you want to pay attention carefully. Again, we notice that there's both a horizontal stretch and a horizontal shift, so we're going to have to factor out that too. You should be good at this by now. This can be -3 cotangent. You pull out the 2, get x minus, pull out 2 from -pi, you get -pi over 2. And then we have -2. So again, we're going to try this with the tabular method, with a table, and then we're going to try this using just kind of understanding the transformations and understand what the cotangent looks like. So let's start off with the basics of a cotangent function. If you define it from 0 to pi, I don't know if you remember, it started with an asymptote, it ends with an asymptote. It goes high, 0, low. And then you just fill in the values in between. So what are some of the transformations? Well, we have a couple things going on. We have a vertical stretch of 3, so and x-axis reflect. So we'll multiply by -3. We also have a vertical shift down of 2, so that's down 2. We have a horizontal compress of 2, so that's divide all the x values by 2. And then we also have a horizontal shift right pi over 2. So we're going to shift all the x values right pi over 2. So you know how to do the transformations, and again, I'm going to go very quickly. Okay, now that we're done, you want to check and make sure that when we graph our final function, we're going to have an asymptote at pi over 2, and at pi, we're going to have another asymptote. And in the center, we'll have 3 pi over 4, comma -2. That's going to be kind of like our new 0. So we'll see what that looks like. I want to show you guys the other method, which is just looking at the periodicity and some of the transformations of the cotangent function. We're going to start with the period, and it's normally pi, but we compressed it by 2, so it's pi over 2. We know that it starts at pi over 2 because of the horizontal shift. Pi over 2 units later, because that's the period, we should end at pi. So this is actually very similar start to the last one. You do want to keep an interval of 4. So we're going to have intervals of 4, 1, 2, 3, 4. That's going to be pi over 2. 1, 2, 3, 4. That's going to be pi. This is where we're going to start, and this is where we're going to end our first period. I do want to mark out the vertical shifts and stretches. So notice that we have a shift down of 2. So kind of like before, what used to be our center was 0. That's going to be shifted down to -2. And we're going to go, our high would be 3 units up, and our low would be 3 units down. When I say low and high, it's not the max or the min. It's just the coordinate in between the 0 and the asymptote. So we're going to use, but we're going to use those as a reference for this. Cotangent, if you remember, it starts on an asymptote. So tangent starts on a 0 or the center. This one starts on an asymptote. So when you graph this, wherever we start, that's where our asymptote's going to be. And it's going to end on an asymptote right here. That's super important. Every pi over 2 units, so if we go pi over 2 units back, there's going to be another asymptote here. This one's a little bit harder to see. So we have asymptote at x equals 0, x equals pi over 2, x equals pi, and then let's even count back another set down here. So this would be at x equals -pi over 2. So we just laid out the framework for asymptotes, and smack in between each asymptote, it's going to be at 0. So here at pi over 4 and 3 pi over 4, it's going to be centered at 0. But the thing is, the 0 shifted down 2 units. So this is kind of like our acting 0. This is kind of like our acting 0. This is our acting high, and this is our acting low. So when you graph it, you want to make sure that it corresponds to the new 0. So these are zeros right there, right there, right there, and right here. You also want to remember that cotangent is typically a decreasing function, okay? Typically, so cotangent is typically decreasing. But we're not dealing with a cotangent, we're dealing with a negative cotangent. So to trip you up, now it's back to increasing. So instead of going down from 1, -2, -5, it's actually going to go up from -5, -2, 1. So we have something like this. Again, so it's going to be increasing, increasing. So we have our 2 periods. You can check it with our values. Again, we said at pi over 2 and pi, we should have asymptotes. So at pi over 2 and pi, we should have an asymptote. If you compare some of the values, at 5 pi over 8, we had -5. So 5 pi over 8, that's right there, we have -5. At 3 pi over 4, we have -2, and at 7 pi over 8 we have 1. That's that coordinate right there. Okay, so the table method only gives you 1 period. Domain, what's the domain of this function? Well, let's look at all the vertical asymptotes. We have -pi over 2, 0, pi over 2, pi. So let's just start writing those. X cannot equal -pi over 2, 0, pi over 2. And you notice that it's increasing or every pi over 2 units. So we're going to make up a formula, pi over 2 plus n times pi over 2. Actually, you could just say n times pi over 2. That's even easier. Range, you notice that it goes from negative infinity all the way to positive infinity. So the range of all of these will always be all real numbers.